Let me ask you something, and I want you to really sit with this question, because it's not a trick question, it's not a riddle. It's one of the most genuinely disturbing things that comes out of our best understanding of physics. If you fell into a black hole, a big one, a really massive one, would you know? Would you feel it? Would there be a flash of light, some kind of shudder, some moment where the universe taps you on the shoulder and says, "Hey friend, you're done. This is it"? The answer, according to general relativity, is no. You would feel absolutely nothing. You would cross the most extreme boundary in the known universe, a threshold beyond which not even light can escape, and you would not feel so much as a breeze. You might be reading a book. You might be thinking about what you had for breakfast. You might be looking out the window of your spaceship, admiring the stars, and the stars would still be there, and you would feel perfectly fine, and you would be, in every meaningful sense of the word, already dead. You just wouldn't know it yet. Now, that statement alone is enough to disturb most people, and it should be. But here's the thing. That's not even the most disturbing part of what black holes do to our understanding of reality. That's just the opening act. The real crisis, the thing that kept me and Stephen Hawking in a kind of intellectual war for almost 3 decades, goes much, much deeper than that. It goes to a question about the fundamental nature of information itself, about whether the laws of physics that we've built up over centuries, the laws that we use to understand atoms, molecules, the evolution of stars, the structure of space and time, whether those laws are even self-consistent in the presence of a black hole. Let me start from the beginning, because to understand why this is such a crisis, you first have to understand what a black hole actually is. Not the pop science version, the real version. A black hole is a region of space-time where gravity has become so intense that the escape velocity, the speed you would need to move in order to get out, exceeds the speed of light. Now, since nothing can travel faster than light, nothing can get out. Not matter, not radiation, not a signal of any kind. There is a surface surrounding this region, a mathematical surface, not a physical wall or a membrane, just a location in space, and that surface is called the event horizon. The event horizon is the point of no return. Here's what's crucial to understand. The event horizon is not where the crushing begins. The singularity is in the middle of the black hole, and that's where space-time curvature becomes infinite. That's where things get ripped apart. But the event horizon? For a sufficiently large black hole, the event horizon is just a place. It looks like empty space. It feels like empty space. There's no sign on it that says, "Warning, you are about to die." There is nothing there. Now think about that. Think about a black hole, the mass of, say, 1 billion suns. The event horizon of something like that would be enormous, and the curvature of space-time at that horizon would be gentle. You know why? Because the bigger the black hole, the more spread out the event horizon is. And tidal forces, the forces that come from the difference in gravity between your head and your feet, those forces are actually weaker for a bigger black hole at the horizon. A bacteria wouldn't notice the tidal forces at the horizon of a stellar mass black hole, but neither would you notice them at the horizon of a supermassive black hole. So you're in free fall, you're drifting, you cross this invisible line, nothing happens, no fireworks, no rumbling, no sensation at all. And somewhere on the other side of that line, at some point in your future that is now unavoidable, you will hit the singularity and it will be over. But here's the chilling part that I keep coming back to. There is a moment before the singularity, after the horizon, where you are fundamentally separated from the rest of the universe. Every photon you send out, every signal you try to make, every cry for help goes inward, not outward. The outside universe can never know what is happening to you. And this is not a limitation of technology. It is not a limitation of signal strength. It is built into the geometry of space-time. You have crossed into a region where cause and effect are fundamentally severed from the outside. You are gone, and no one outside can ever confirm it. No information about what happens inside the black hole can ever reach the outside. And that is where our real crisis begins. Let me tell you about a man named Jacob Bekenstein. In the early 1970s, Bekenstein was a young graduate student, and he did something rather remarkable. He suggested that black holes have entropy. Now, entropy is a measure of disorder, a measure of how many microscopic ways a system can be arranged while looking the same on the outside. And physicists at the time laughed at this idea because a black hole was supposed to be the simplest possible object in the universe. By what's called the no-hair theorem, a black hole is completely characterized by just 3 numbers: its mass, its electric charge, and its spin. That's it. 3 numbers. That's all there is to know about a black hole from the outside. It has no hair, no extra information, no complexity. So how could it have entropy? But Bekenstein pushed forward, and a young physicist named Stephen Hawking I want you to picture this guy, brilliant beyond measure, already in the early stages of the disease that would eventually confine him to a wheelchair, this mind working at full, extraordinary capacity. Hawking did a calculation, and the calculation showed something nobody expected. Black holes radiate. This is Hawking radiation. It comes from quantum mechanics. It comes from the fact that the vacuum of space is not really empty. It's a sea of virtual particle-antiparticle pairs, constantly popping in and out of existence, appearing for a tiny moment and then annihilating each other. Near the event horizon, occasionally one of these pairs separates. One particle falls inward, the other escapes outward. And from the point of view of an observer far away, the black hole appears to be emitting radiation. Now, I want to be very careful here, because this is where the subtlety lies, and the subtlety is everything. That radiation, the Hawking radiation coming out of the black hole, Hawking showed that it was thermal radiation. It was random. It was the kind of radiation you'd get from any hot object. It carried no information about what fell into the black hole. And that's the bomb. Think about what this means. You take a book, a beautiful novel, a unique piece of human expression, and you throw it into a black hole. According to Hawking's calculation, what comes back out in Hawking radiation over billions and billions of years is just random heat. The specific content of the book, the specific arrangement of letters and words and ideas, is gone, permanently, irreversibly. The universe does not remember. And the reason this is a catastrophe, not just for me, not just aesthetically, not just because it's sad to lose a nice book, the reason it's a genuine physical catastrophe is because of something called unitarity. Unitarity is one of the most fundamental principles of quantum mechanics. It says that information is always conserved. It says that the evolution of a quantum system is always reversible, in principle. If you know the exact quantum state of a system right now, you can calculate what it was in the past. Everything that happens can, in principle, be run backwards. The quantum state of the universe at one time completely determines the quantum state at any other time. Nothing is ever truly lost. Hawking was saying that black holes violate this principle. Hawking was saying that you can take a specific, complex quantum state, throw it into a black hole, wait for the black hole to evaporate, and at the end of the day, you're left with nothing but thermal garbage that contains no memory of what you put in. He was saying that quantum mechanics breaks down, that the laws of physics, as we know them, cannot be correct in the presence of a black hole, and he was very, very confident about this. In 1997, Hawking and Kip Thorne made a bet with John Preskill. The bet was simple. Does information escape from black holes or not? Hawking and Thorne said no. Preskill and I was not technically in the bet, but I was very firmly on the side that says the information has to come out. Preskill said yes. Now, you have to understand, at this point in the 1980s and early 1990s, most of the physics community was on Hawking's side. He was one of the most celebrated scientists alive. His calculation was technically beautiful, and the people saying the information had to come out, people like me, like Gerard at Hooft, we didn't have a complete mechanism. We didn't have a full explanation for how it worked. We just knew that if Hawking was right, the consequences would be devastating, in a very precise technical sense. It's not just that losing information is untidy. In 1984, Tom Banks, Michael Peskin, and I wrote a paper showing that if information really is lost in black holes, then the temperature of the vacuum of space, the background temperature of empty spacetime, should be on the order of the Planck temperature, which is 10 to the 32 Kelvin. The background temperature of empty space should be ridiculously, catastrophically, universe-destroyingly hot, and we don't observe that. So something in the argument has to be wrong. The universe that Hawking's information loss scenario describes is not the universe we live in. So I started thinking hard about how to resolve this, and what I came up with, together with my colleagues Lenny Thorlacius and John Uglum, was something we called black hole complementarity. And this is where the story gets really interesting, and also deeply strange. Here's the setup. You have two observers. Let's call them Alice and Bob. Alice is falling into the black hole. Bob is staying safely outside, watching from far away. Now, what does Bob see? According to quantum mechanics, from Bob's point of view, Alice's information never actually crosses the event horizon. As Alice approaches the horizon, from Bob's perspective, time slows down for her. The signals she sends get increasingly redshifted, increasingly stretched out. The last signals reach Bob over an incredibly long time. Her image, from Bob's perspective, gets frozen near the horizon, gets thermalized, and eventually, very gradually, that information gets radiated back out in the Hawking radiation, scrambled, encoded in an incredibly complex way. But in principle, it's there. Bob can reconstruct it. Now, what does Alice see? Alice, falling freely in free fall, crosses the horizon without noticing anything. The equivalence principle. Einstein's principle that says you can't tell the difference between free fall and floating in empty space. That principle says Alice should experience nothing special at the horizon. She goes right through. She carries her information with her into the interior. Here's the paradox. The information is in two places at once. It's both outside the black hole, encoded in the Hawking radiation Bob is collecting, and inside the black hole with Alice. And that violates a sacred principle of quantum mechanics, the no-cloning theorem, which says that you cannot copy quantum information. You cannot make a perfect duplicate of a quantum state. But here's how complementarity resolves it. The key insight, and this is the part that requires a real rewiring of how you think about reality, is that Bob can never verify the duplication. Bob sees the information come out in Hawking radiation. But Bob can never jump into the black hole and ask Alice, "Hey, do you also have the information?" Because if Bob jumps into the black hole, he is now also inside and can never communicate with his past self outside. And if Bob stays outside, he can never ask Alice anything. The two observers are causally disconnected. They can never compare notes. The duplication can never be experimentally verified. So complementarity says the universe is saved from inconsistency, not by making the situation consistent. The duplication is real, the information really is in two places, but by making it unobservable. Nature protects the no-cloning theorem not at the level of physics, but at the level of what any observer can actually measure. I know, that sounds like a cheat. But this is actually deeply in the spirit of quantum mechanics itself. Remember the measurement problem. Remember the double-slit experiment. Quantum mechanics has always been a theory about what observers can observe, not about what really happens in some observer-independent sense. Complementarity is, in some ways, just taking that lesson seriously and applying it to black holes. Now, for about 15, maybe 20 years, this was the picture. And it was a good picture. And it led to one of the most remarkable ideas in modern physics, the holographic principle, which deserves its own explanation because it's genuinely one of the most beautiful and mind-bending things I've ever thought about. The holographic principle says that all the information contained in a region of space is encoded on the surface that bounds that region, not in the volume, on the surface. Two-dimensional information encoding three-dimensional reality, like a hologram. Where does this come from? It comes from thinking carefully about entropy and black holes. Bekenstein and Hawking showed that the entropy of a black hole is proportional to the area of its event horizon, not its volume. This is deeply strange. Usually entropy scales with volume. A bigger box has more entropy because there are more places to put things. But a black hole's entropy scales with area, which means the maximum amount of information you can store in any region of space is proportional to the surface area of that region, not its volume. Think about that. Think about this room, or wherever you're watching this. The maximum information content of the space around you is not determined by how big the room is. It's determined by the area of the walls. It's as if the walls are a giant holographic screen on which everything inside is encoded, and what we think of as three-dimensional reality is just a projection, just an image. A very convincing image. The most convincing image in the universe, but an image nonetheless. This was developed further by Juan Maldacena, who in 1997 found a precise mathematical realization of this idea in what's called the ADS-CFT correspondence. It's a duality between a theory of quantum gravity in a curved spacetime and an ordinary quantum field theory on the boundary of that spacetime. No gravity, no extra dimensions, just a quantum field theory on the boundary, and yet it perfectly encodes everything that happens in the bulk, including the behavior of black holes. And in Maldacena's framework, the evolution of the system is manifestly unitary. Information is conserved, period, full stop, which means that Hawking had to be wrong. The information does come out. In 2004, Hawking gave a talk at a conference in Dublin and conceded the bet. He paid John Preskill with a baseball encyclopedia, and this was deliberate on Hawking's part, choosing an encyclopedia from which information can be retrieved at will. It was very Hawking. Even in defeat, he was making a point. But I want to be honest with you, because I think the story is more complex than Susskind won, Hawking lost, case closed. The question of how exactly the information comes out is still not fully resolved. We know it comes out. The ADS-CFT duality makes this almost certain, but the mechanism, the precise physical story of what happens at the horizon, how the information gets encoded in the Hawking radiation, what it actually looks like from the inside, this is still deeply contested. And in 2012, a group of physicists, Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, the AMPS group, blew things open again. They constructed a very careful argument that shows the following. If information comes out of a black hole in the Hawking radiation, and if that radiation obeys the laws of quantum mechanics, and if the interior of the black hole exists and is the smooth, uneventful place that general relativity says it is, then you get a contradiction. A genuine logical contradiction. You can't have all three. Something has to give. Their proposal was that the interior of the black hole is not smooth, that if you fall into a black hole, you do not pass through the horizon gently, undisturbed. Instead, you hit a wall of fire, a firewall, a region of energetic radiation at the horizon itself that incinerates you. No quiet death beyond the threshold. You burn up exactly at the point of no return, which would mean that the chilling statement I started with, "You won't realize you're dead," is wrong. Or rather, it raises the terrifying possibility that you might realize you're dead, but only for a fraction of a second before you're vaporized. Now, I think the firewall argument is serious. I've had to take it seriously. I've written about it extensively, but I also don't think it's the final word. My own view, which I developed partly with Juan Maldacena under the slogan ER equals EPR, is that the resolution involves entanglement and geometry in a deep way. ER is the Einstein-Rosen bridge, what you might know as a wormhole. EPR is the Einstein-Podolsky-Rosen paradox about quantum entanglement. And the claim is that these two things, wormholes and entanglement, are not just analogous. They are the same thing. Quantum entanglement between two systems is equivalent to a geometric connection, a wormhole, between them. The Hawking radiation outside the black hole is entangled with the interior. And this entanglement is not just a statistical correlation. It is, in some deep sense, a geometric connection. The outside and the inside are connected by entanglement that is as real in its own way as a wormhole. If this is right, it changes the nature of the firewall paradox. The firewall paradox assumed a kind of monogamy of entanglement, that the Hawking radiation outside can only be entangled with the interior, not with earlier Hawking radiation. But if the geometry itself is built out of entanglement, then the notion of what counts as inside and outside becomes much more subtle, and the paradox may dissolve. I'm not going to tell you this is settled. It isn't. This is the frontier. This is physics being done right now, in real time, at institutions around the world. The best minds in theoretical physics are working on this. And the reason it matters, the reason we should care, beyond the intrinsic beauty of the problem, is that it sits right at the junction of the two great theories of the 20th century, quantum mechanics and general relativity. These two theories are both extraordinarily well tested, both work with unbelievable precision in their respective domains, and yet they are deeply inconsistent with each other. They use different mathematical languages. They make different assumptions about the nature of reality. They cannot both be fundamentally correct as they stand. One or both of them needs to be revised at the deepest level. And the black hole, this extreme environment where both theories must apply simultaneously, is the laboratory where those contradictions become visible. Stephen Hawking understood this better than anyone. That's why, despite everything, despite the fact that his conclusion was almost certainly wrong, the fact that he raised the information loss paradox was one of the most important contributions to theoretical physics in the second half of the 20th century, because it forced us to stare directly at the contradiction. It forced us to confront the fact that something is deeply, fundamentally broken in our picture of reality, and to start doing the hard work of figuring out what. Now, let me come back to where I started. Let me come back to the falling astronaut. Because here's the final twist. Here's the thing that I find most astonishing about all of this. From Alice's perspective, Alice falling into the black hole, general relativity says she passes through the horizon in perfect comfort. She notices nothing. She continues on in free fall, reading her book, thinking about breakfast. She will eventually reach the singularity, and that will be the end. But at the horizon itself, nothing happens. From Bob's perspective, Bob watching from outside, Alice never quite makes it. Her image gets stretched and dimmed and frozen near the horizon, and over vast stretches of time, her information gets radiated back in Hawking radiation. Two completely different stories, both of them, in some sense, true for their respective observers. And yet there is no inconsistency because no single observer can verify both stories. The universe permits both descriptions simultaneously as long as the two observers are causally separated. This is what I mean when I say that black holes require a rewiring of how we think about reality. We are used to thinking of reality as objective, as something that exists independently of who is observing it. A thing either happened or it didn't. Alice either crossed the horizon or she didn't. The book either made it inside or it didn't. But if complementarity is right, and I believe it is, at least in its essential spirit, then this objectivity is an illusion, or at least a very localized, parochial thing. Reality is observer-dependent in a much more radical way than even quantum mechanics taught us to accept. Different observers, in different reference frames, separated by an event horizon, can have equally valid, completely incompatible descriptions of the same sequence of events. The universe is not a collection of facts, it is a collection of perspectives, and the black hole is the place where we were forced to learn this lesson. And there's one more thing. One more dimension to the strangeness that I want to leave you with. Think about what we said earlier about the future of the universe. We live in a universe that is expanding, and the expansion is accelerating. Everything is flying away from everything else. In about 1 trillion years, the only galaxy that will be within reach of our observations will be our own. Every other galaxy will have passed beyond what's called the cosmological horizon, a kind of event horizon for the entire universe, beyond which the recession velocity exceeds the speed of light, beyond which no signal can ever reach us. All the astronomical information we have about the rest of the universe, the billions of galaxies, the vast cosmic web of matter and radiation, the evidence for dark matter and dark energy, and the cosmic microwave background and the whole magnificent structure of cosmology, all of it will be, in the causal sense, gone, unreachable. And any civilization that arises 1 trillion years from now will look out and see only their own galaxy surrounded by darkness, and they will conclude, because they have no evidence to the contrary, that the universe is nothing but this. They will be wrong, and they will have no way of knowing they are wrong. Information about the origin and structure of the universe will have effectively been lost, not into a black hole, but across a cosmological horizon. The universe will be doing to future astronomers exactly what black holes do to information. It will hide the past behind a boundary that no signal can cross. And we, right now, in this brief window of cosmic history, where the universe is still young enough and small enough that we can observe its full richness, we are lucky. We are cosmically, extraordinarily, improbably lucky to be here now, asking these questions while there's still information to be gathered. The physics of black holes is not just about black holes. It is about the nature of information. It is about the nature of reality. It is about what it means to exist, to observe, to know. It is about whether the laws of physics are self-consistent and what happens when two of our most powerful theories look each other in the face and produce a contradiction. We don't have all the answers, not yet. But the questions are beautiful, and that's why we keep going. That's why this is worth doing. The universe won't realize we're asking, but we will.